Hello. Here we will use the properties of the scalar product of coordinate vectors to generalize a notion, to make it abstract. To extend this nice story of scalar products, corresponding notion of length, orthogonality, perpendicularity, and all that to arbitrary vector spaces. So let's assume that V is just a vector space over real numbers. And then the scalar product V will be a function which as arguments has pairs of vectors from V and gives takes values in real numbers. And just the properties of coordinate scalar product are now the definition of this arbitrary abstract scalar product. So linearity in each argument, additivity equation first for the first argument, and then scaling stability for the first argument. So C is a number, real number, x, y, and z are vectors from the vector space. The same for the second argument, which is actually redundant due to next condition we're going to put. But for the bookkeeping sake, it makes some sense. The last condition which makes the second linearity redundant is the symmetry condition. Linearity in the first will be translated into linearity in the second. And the last condition of positive definite nature of this scalar product is that what we might call the squared norm of a vector x, which is by definition the scalar product of x with itself, is never negative, and it is only zero when x itself is a zero vector, So that is, we might just call abstract scalar product on an arbitrary vector space V. Let's look at the main example, at the reason for doing this abstraction in the first place. The vector space will be big, will be infinite dimensional, so there is no way of representing this vector space as a space of coordinate vectors. Nevertheless, such functions are quite possible. Let's imagine the space of continuous functions on a closed interval, say unit interval starting at 0, ending at 1, with real values. So our vectors are this type of functions, continuous functions on the unit interval with real values. And we can add these vectors, we can add functions, we can multiply them by numbers, they will still be continuous. And then define the scalar product by a formula. So the result of the scalar product on f and g is just the definite integral through this interval of the product of two functions. Checking the properties which will make this scalar product is easy, is straightforward. So if the if the first of the two functions, if f is the sum of two, then the integrand is the sum of two products, and the integral is the sum of two integrals. In each of them will be scalar product. So I'm just delegating these precise computations to you, but they are very straightforward, still rewarding. The same with scaling. In any of the arguments, we could take the scaling coefficient c out of the integral, and that will just prove this equation. And the same for the other, but yeah, it's easy to notice the symmetry because the product f and g is symmetric in f and g. The most interesting is this condition, which says that the integral of square of any function is always non-negative. And it's easy to convince oneself in that, because we're integrating something which is above the x-axis all the time, well, above or touching it, never below. And then the area under this curve, which is something like that. So here's the interval, and the graph of f squared, whatever f is, will have to be above. And so the area will always be positive, or negative at least. And then if it is 0 for continuous function, it means that the function has to be constant 0. So that is the most non-trivial statement, but it is still a relatively straightforward statement from calculus. Non-continuous functions can still be not totally 0, but have 0 integral, like delta functions, but continuous functions are free from these pathologies, and we must have f of x being 0 itself. So that is the positive definiteness of this scalar product. Let's look at examples, some simple examples. Let's take two easiest continuous functions, namely two polynomials, degree 1, degree 0 first, constant function 1, and then degree 1 polynomial, just identity function x. So what will be their scalar product? It will be the product, the integral of the product of two functions, namely the integral of x over this unit interval, and it is easy to evaluate. This is just the prime function, a prime function for x, which is, say, x squared over 2, evaluated at 1 and at 0, and the difference of values is the result. The difference of values is just 1/2. In the same way, we can compute the scalar product of the first function with itself. That will be just the integral of the constant function 1 over the unit interval, which is just 1. And the scalar product of the second function with itself, the squared norm. So this becomes of length 1. That's what this computation is saying, that the function f we have here is a unit vector in the vector space. So computing the norm of this, first scalar product, we have to integrate x squared over this unit interval. Again, prime function evaluated at the endpoints of the interval is our answer. It will be 1/3. So the norm here, norm of g, of this g, is 1 over the square root of 3. And finally, we can compute the angle between the two. Cos of that angle is the ratio of the inner product, scalar product between the functions, over their norms. So we have 1/2 upstairs, we have 1, and then 1 over square root 3 downstairs, which comes down to square root 3 over 2. And it's easy to find what alpha is if you don't remember it from something more elementary, but alpha is nothing but pi over 6. So that is a really weird answer, but these were already weird answers, saying that these functions can be measured, how lengthy they are with respect to this scalar product. These are the results, and even we could see how non-orthogonal these two functions are. The angle between them with respect to this, again, measure given by scalar product is pi over 6. More of that type of computations is to come. So see you later.